Okay, this is the first video on gravity and orbits, which will really sum up everything we've learned about mechanics in the first part of this class. What Newton's big idea in the 17th century is that the same force that makes things fall on Earth is responsible for keeping the planets in their orbits, which was really the first example of a unified theory. But what Newton said is that any two massive objects, meaning mass is not zero, will attract each other, m1 and m2. They will experience forces toward each other. Those will be equal and opposite, Newton's third law right there. And the magnitude is given by the equation gm1m2 over r squared. G is a constant. Its value is 6.67 times 10 to the negative 11 Newton meters squared per kilogram squared. You don't need to memorize that value. You do need to know where to find it. R is the distance between them. Now, that equation is strictly true only when these two are point masses. But it also works when they are spherical. So, if they're spheres, r is the distance between the centers. And that's fairly simple. Now, there's an idea called superposition, which you should have seen last year, or you did see last year, you should remember it, which is the idea that if you have three or more objects, if you want to find the net force on one of them, you find the force due to each of the other objects, and then you add those forces up. It's all very simple. So in this example, which is problem 12 from your textbook, you have four particles. Particle B is at the origin. And draw axes. Particle A is located 50 centimeters above particle B. Particle C is located 80 centimeters away over here, and particle D is 40 centimeters away there. And those have masses given. And the result is B will be pulled by all three of these. I'll call that FA, FC, and FD. And what we're going to do is we're going to find the magnitudes of FA, FB, and FC using Newton's law of universal gravitation, and then we'll add them all together as vectors. So FA equals G, which is 6.67 times 10 to the negative 11 Newton meters squared per kilogram squared, times the mass of A, which is 400 kilograms, times the mass of B, because it's an interaction between A and B, is 350 kilograms, and the distance between them is only half a meter. We square that. If you put this in your calculator, you get 3.74 times 10 to the negative fifth newtons. Notice gravity is very, very weak. Then we can find FB, where we use the same equation, just different mass and distance. The mass of, or FC, sorry. The mass of C is 2,000 kilograms. B is still 350. And the distance now is 0.8 meters. And so FC works out to be 7.30 times 10 to the negative 5 newtons. And if we do a similar equation for FD, we find that FD is also 7.3 times 10 to the negative 5 newtons. Notice that C and D are equal and opposite, so they cancel out. And so that net force just happens to be FA, which is 3.74 times 10 to the negative fifth newtons, upward. And there is our answer. Now, there's also, you need to be able to calculate the gravitational force on something inside the Earth, which is quite interesting. So, if we consider a spherical shell, it has a total mass capital M, has a radius r, and it's hollow in the center. Now, if we put a small mass, little m, anywhere inside that shell, it will not have any force on it. And that sort of makes sense, because if you look at how much mass is over here, there's a lot more mass over here than there is over here, but it's also on average farther away. Now, that's a very hand-wavy argument. If you want to prove it, you can do a whole lot of integration in calculus, but you don't need to. This is one of those things you can just take your textbook's word for it. So if m is inside the shell, no force at all. But now we put m outside the shell, and let's call the distance from the center of the shell to m little r, as opposed to capital R, which is the radius of the shell. In this case, the force on the small mass is going to be g times the product of the masses divided by r squared, just as if all the mass of the shell was concentrated at its center. So that makes a lot of apparently very thorny problems quite easy. And we'll use this idea again when we get to electrostatics, so please don't forget it. So let's imagine that we are drilling down into the Earth, very deep mine, and we want to find out what happens to the gravitational force on something inside the Earth. So what we'll do is we'll say here's the Earth, mass capital M, radius capital R, and what we want to do is find the force that the Earth exerts on a small mass little m located a distance little r away from the center of the Earth. Now the first thing we get from the spherical shell rule is that all the mass outside that dotted line, that's a series of spherical shells that are all outside the small mass. The small mass is inside all those spherical shells. And so none of the mass outside the dotted circle matters. And then what we say is all the mass inside the spherical shell, inside that dotted circle, can be treated as a spherical. So the mass inside the dotted line does matter, mass outside doesn't. And so if what we have to do is say the gravitational force on the small mass m is g times little m times, I'm going to call this m inside, the amount of mass that is contained inside this circle. So and so we have to ask, how much mass is that? And to answer that question, we need to know something about the interior of the Earth. We are going to assume for the moment that the Earth is of uniform density, which is not a good assumption, but we'll make it anyway. So I'll put that in red letters so that we know that it's not a good assumption. And we can say that the density of the Earth is the mass divided by its volume. So the mass of the Earth divided by the volume, which is 4/3 pi r cubed. And then the mass contained inside is equal to the density times the volume of the small sphere, 4/3 pi little r cubed. Plug in rho, and we have m over 4/3 pi big R cubed times 4/3 pi little r cubed. Lots 4/3 in the pi cancels, and so this is m times the ratio r to big R cubed. And that means that the force of gravity, when we plug this expression in for m inside, is g m over little r squared times little r cubed over big R cubed. And we end up with gmm over big R cubed times little r, which is very interesting because it means that the further you go down into the Earth, little r gets smaller and gravity gets weaker. And if you had a cavity at the center of the Earth, everything in that cavity would be completely weightless, which is kind of cool. It would also be really, really hot, but that's a separate issue. And that is the end of the video, apparently. So, next time we'll talk about orbits. What you need to know is how to calculate the gravitational force using superposition or the spherical shell rule.